In this video, I want to review some U substitution rules, starting with a few indefinite integrals and then moving to definite integrals. So I don't have bounds here, I just need to find the antiderivative here. The first question I should ask myself is, who is U? And the answer to that question is, well, try a couple things, but usually looking for the composition of functions is helpful. Because if I let U be equal to that guy right there, then this whole term would just be U to the fourth, and I would know how to integrate that. And what I'm already looking at as I'm looking into the future here, I need to get rid of that 2x and that dx. And if I take the derivative of x squared plus 3, that's going to get me 2x dx. So I think that's a good candidate for who U should be, right? So if I take the derivative on both sides, du is equal to x squared just turns into, I bring down the 2 multiplied by the exponent and subtract 1 from it, so that's just x to the first. The derivative of any constant is 0, so that's just 2x dx, which is great because that's precisely what I still need to replace here, right? Currently, this integral looks like U to the fourth, if I just bring this blue stuff to the front, times 2x times dx. And 2x dx is precisely the same thing as du, so I'm going to make that substitution there. So this is really asking me to take the integral of U to the fourth du. So from here, that du and that integral sign is just telling me to take the antiderivative of whatever's in between there. So if I use a reverse power rule here, I could add 1 to the exponent and divide by it. But remember, since this is an indefinite integral, there could have been any constant there, so I just need to compensate for that with a plus c. Now, of course, they gave me the problem in terms of in terms of x, so I just need to substitute back in for x. So my final answer here is x squared plus 3 to the fifth over 5 plus c. Now, if this was a definite integral, I would just evaluate it from my bounds there, but it's not, so I could leave it right here. This is the general antiderivative of my original function. And you could always check by taking the derivative using the chain rule if you wanted to. For number 2, we could find another indefinite integral. I want to integrate dx over 5 minus 3x. Now, if you're having trouble seeing what this is the same as if I had the integral of 1 over 5 minus 3x dx, but they represent the same thing. And it really looks like there's only one good candidate for u here, and that's that denominator. So I'm going to let u be equal to 5 minus 3x. And if I differentiate, the constant goes away, and if I bring down that 1, that's negative 3x to the 0, but remember x to the 0 is just 1. So that negative 3x turns into negative 3 times dx. So you got to ask yourself, what am I still trying to replace? Well, I replaced that denominator right there. So right now I have the integral of 1 over u dx. So really I still need to get rid of that dx right there. This expression is pretty close. I noticed that if I could just divide out the negative 3 divided by negative 3 is just 1, so I'd be left with 1 dx. And I'm going to write that as a negative 1/3 being multiplied, just because I know it's going to help me out later. And I'm going to take that value and just substitute it in straight for dx there. So really, this is the integral of 1 over u times negative 1/3 times du. You don't need the parentheses here because it's all linked by multiplication. But right now this is a little chunky to look at. For a constant, I could just pull it out, same thing as my derivative rules, and write it on the outside. And now I can take the derivative here. The antiderivative. The problem is, I don't really know how to work with 1 over u. You could try to make it u to the negative first and use a reverse power rule, but that's not going to work. So you need to recognize that this is one of those special antiderivatives, right? That 1 over u, that's the derivative of ln of the absolute value of u plus c. Of course, I need to substitute back in. So I have my final answer is negative 1/3 ln, the absolute value 5 minus 3x plus c. Now wait for you to check yourself, if you forget about these absolute values here. The reason the absolute values are here is just because my domain is not constrained for 1 over u, but for the ln function, remember that graph looks like this. So it's only defined for positive inputs. That's just why I have those absolute value bars there. So don't try to get hung up on that. The idea is the relationship you need to see, if that's my answer, is that if I have a function ln of x and I differentiate it, I get 1 over x. So that if I start with something that looks like 1 over x and I anti-differentiate, I should end up back with something with an ln. So just keep that in mind. So for number 3, something a little bit tougher to look at, I have x over the cube root of 1 minus 3x squared dx. Now there's, again, really only one candidate for you. It looks like all that ugly stuff in the bottom right there. So whatever you want to get rid of to make your life easier, that's who u is going to be. Again, if I take the derivative, I get du equals, if I bring down that exponent, negative 6 x to the first dx. And I ask myself, what do I still need to get rid of? Well, here's my integral, right? I've got the integral of x over the cube root of u dx. I still have an x I need to get rid of, and I still have a dx I need to get rid of. Because again, if you're having trouble seeing this, this is the same thing as if I write 1 over the cube root of u times x times dx. Right? If I wanted to simplify that all as one fraction, I would put those all over 1 and multiply the numerators and the denominators. But I'll leave it like this to recognize that if I can get an expression that looks like that, in terms of du, I can make a substitution. So again, I'm going to just divide out the negative 6. And I get negative 1/6 du is equal to x dx. Lo and behold, that's exactly what I need, right? X dx. So I'm going to substitute in negative 1/6 du there. So really, this is the integral of 1 over the cube root of u times negative 1/6 du. You don't need to write this step if you don't want to. I always jump to just pulling the constant on the outside and thinking about how I could rewrite it to make it easier to take the antiderivative. Well, remember the cube root of u to the first. If I want to rewrite that as power over root, that's u to the 1/3 in the denominator. But it doesn't really help me out in the denominator. But if I bring it to the numerator, remember I would just need to make the exponent negative. Now I know how to deal with that. What I'm going to do is I'm going to add 1 to the exponent and divide by my new exponent to use the reverse power rule to take the antiderivative. This is where things get a little hazy, so you just need to be careful with your fraction rules. If I take negative 1/3 and I add 1 to it, that's the same thing as if I add 3/3 to it. So that's the same thing as 2/3. So I have u to the 2/3 divided by 2/3. Now, you could write a division of a fraction, but remember dividing by a fraction is the same thing as multiplying by the reciprocal. So I'm just going to multiply by 3/2 instead, just to save myself a little bit of work. Remember, there should be a plus c because this is the general antiderivative, or the indefinite integral. If I simplify a little bit, I can multiply my numerators here and multiply my denominators there. This is really like negative 3 over 12 u to the 2/3 plus c. And negative 3 over 12 just simplifies, if I divide those both by 3, negative 1/4. And instead of writing u, I'll make my substitution back right here, 1 minus 3x squared to the 2/3 plus c. Again, don't worry about plugging in here. We'll get to some definite integrals in a minute, but this is as far as we need to go for this indefinite integral. But let's take a look at some trig now. That's enough polynomials. But what if I had something like the integral of cosine of x times sine to the 6th of x dx? Well, it might not be immediately obvious who u should be, right? I've got a cosine and I've got a sine, but I noticed that this is sine to the 6th x. And notation-wise with trig, normally we write the exponent next to the trig function. I'm actually going to write that a little bit differently, just to make it more obvious who u is. I'm going to write that as sine of x to the 6th dx. The reason I write it like this is because this whole chunk I don't know what to do with. Sine of x to the 6th. That's a composition of functions there. If this was just u to the sixth, I would know how to deal with that. So the reason I'm going to let u be sine of x is two things. It's the composition of functions I see here, and if I make that u to the sixth, I'd be able to take the antiderivative there. But the other reason is, what I still need to get rid of is cosine of x. And I know if I take the derivative of sine of x, I'm going to end up with cosine of x, so I'll be able to make that substitution. So try to have a little bit of foresight when you're picking who u is, because that's going to help you from having to go back and pick something else for u. So if I differentiate, the derivative of sine x is just cosine of x dx. And lucky me, that's exactly what I am trying to get rid of. So I'm just going to take those two guys, replace them with du, and this is very cleanly just the integral of u to the sixth times du. Now I am in business. I could add 1 to the exponent, divide by it, and of course there's a constant there. Now the only thing you need to be careful of is just to make the substitution back in. So really, the integral of cosine x times sine to the 6x dx is just sine of x to the 7th over 7 plus c. And if you don't believe me, you could differentiate just to check your answer. I'm going to do it here just for fun. Right? So let's see. If I take the derivative of this piece right here, well, looks kind of weird. How about I write it like this instead? Because then it's just a constant times something else, and the constant I just bring down. Now, this looks like a good old chain rule, right? I've got an outside function of something to the 7th, and I've got an inside function of sine of x. So remember, it's the outside function times the derivative of the inside. So if I bring down that 7, rewrite the inside, so this is the derivative of the outside, I'll call him, 7 times sine of x to the 6th, times the derivative of the inside. The derivative of the inside there is just cosine of x. Now, a couple of great things happen here. Number one, the constant just goes away, because the derivative of any constant is 0. But also, 1/7 times 7 reduces to 1, and if I bring that cosine of x in front instead, I've got cosine of x times sine of x to the 6th. Oh my gosh, would you look at that? That's exactly what we started with. Right? So you don't have to guess for any of these indefinite integrals. You could absolutely check each of your answers by differentiating as long as you're careful. So let's try a couple more examples. For number 5, let's take a look at the integral of e to the radical x over radical x dx. Now, the thing that immediately jumps out to me is this e to the radical x, and he's going to cause some issues for me. I don't know how to deal with him, but I do know how to deal with e to just some variable. The integral of that is just e to some variable. So my initial thought here is just to try to make that radical x up there equal to u. Now be very careful. That radical x is not the same as that radical x, because really this denominator is like 1 over radical x, because he's in the denominator. So they're not the same thing, so try to be careful there. Now if I'm taking the antiderivative of radical x, I want to rewrite that as an exponent of 1/2. And I'm going to apply the power rule. I'm going to multiply by the exponent, so bring down the 1/2, and subtract 1 from it. So 1/2 minus 2/2 is just negative 1/2. So that's my derivative there. Now this is a lot to take in, right? Let's just rewrite my integral here. I now have e to the u times, I'm going to separate it just to make it cleaner, 1 over radical x dx. So I need to try to get an expression that looks like this with a du in it that I can make a substitution for. And right now it's not immediately obvious, so I'm going to start doing some rewriting. Remember, a negative exponent just means that it's in the wrong place. So I could bring that back down to the denominator, and hopefully that helps me. So 1 over 2 times x to the 1/2. But remember that x to the 1/2 is just the same thing as radical x. So I'm going to rewrite it as radical x, because I see that in my denominator here, so I'm trying to get something that looks like that. Now, if I could get rid of that 2 in the denominator, this would look exactly like what I need it to look like. So I'm actually going to multiply both sides of my equation here by 2. Because if I multiply 2 times 1/2, that reduces to 1. So I'd have 2 du equals 1 over radical x dx, which again, this is always going to be the case for u substitution. You can get something that looks exactly like what you're trying to replace there. And I'm going to make that substitution and keep integrating. So I have e to the u times, that whole expression highlighted in blue there is just du. Now remember, if I differentiate e to the x, I just get e to the x. So if I want to anti-differentiate e to the x, I am still going to get e to the x. So by that logic, the integral of e to the u just turns into e to the u plus c, and I can make my substitution back in. To get e to the u is just radical x plus c. So these exponentials can be a little trickier, especially when you're working with negative exponents. So just be careful with your algebra skills there. The goal is always to just make the integral as simple as possible to look at, and here we were able to do that pretty nicely. Let's try one more example where that happens pretty cleanly. For number 6, I have the integral of cosine of x times sine of x dx. Now you might be looking at this and saying, ooh, this is a lot to take in. I have no idea who u is. So ask yourself, who looks harder to deal with? Is it the cosine of x or the sine of x? To me, it looks like the sine of x. So I'm going to try to constrain my view just to this. Now, let's say I let u be equal to sine of x. If I differentiate this is a chain rule, right? The derivative of sine of something is cosine of something times the derivative of that something. So the derivative of the inside is cosine of x. Now this looks pretty good because I have a cosine of x dx, but I've got all this other weird stuff over here that just doesn't appear in my original integral. So what happens here is I got stuck because I get something with du that I know I won't be able to replace. So instead of trying to rearrange this, because this is really ugly looking right now, I'm just going to go back to the drawing board and I'm going to try something else for u. Maybe if I let u be equal to this term right here would just be sine of u. And then if I take the derivative of sine, I should get something with a cosine, so maybe I'll be able to make a substitution there. So that looks like it's going to be a better choice for me. So that highlighted in yellow, I'm going to make u. The derivative of sine is just cosine. And if you look back to the integral, I need to get rid of a cosine of x and a dx. I've got a cosine of x and a dx. So all that stuff in blue I could just replace with du. So that's going to be a much better candidate for who u should be. So this is just the integral of, I've still got a sine function of u, because I made u that stuff in yellow, times du. And du is just all that stuff in blue, cosine x dx. Well, this is 1,000 times simpler to worry about. The integral of sine is negative cosine. And the reason I know that is because if I differentiate cosine, I'm going to get negative sine. So if I try to reverse engineer this rule, I need something whose derivative is just positive sine. So in order for that derivative to be positive sine, I would have had to have been differentiating negative cosine. So that's just the thought process I have there if I have trouble memorizing the rules. But I'm going to make my substitution back in, and good thing I don't need to evaluate this because this is looking pretty chunky as it is. The integral of cosine x times sine of x is just negative cosine of x plus c. And again, you could always just differentiate to check your answer there. That's in terms of indefinite integrals with the plus c, but let's do a few definite integrals just to get those under our belt. So let's say I gave you bounds now, and something that looked like this. X times radical x squared minus 1 dx. Again, it looks like a pretty good candidate for u is that inside under the radical, because if I had just radical u, again, I know how to deal with that. So I'm going to do all the same steps as an indefinite integral. I'm going to let u be equal to something to make that substitution, take the derivative of it, and try to substitute in. The only difference is I need just an x and a dx, but I have a 2 out in front here, so I'm just going to divide that out, make my life a little bit easier. So I have 1/2 du is equal to x dx. So I'm going to take the integral of, now this light blue stuff is just going to turn into radical u, and all the dark blue stuff, x dx is just the same thing as 1/2 du. All the same rules still apply here with my integration. Nothing changes yet. I'm going to bring out the 1/2, rewrite the radical u as u to the 1/2, and rewrite du. Now again, remember, I add 1 to the exponent. So 1/2 plus 2/2 is 3/2, and I'm going to divide by that exponent. Now, there's no reason to write this step here. I'm just showing you how I get that. Dividing by a fraction is the same thing as multiplying by a reciprocal. So I could really just multiply by 2/3 out here. The reason I'm writing it separate just so that I could recognize I'm allowed to multiply my constants there, and the 2's actually reduce to 1 there. So really I have 1/3 u to the 3/2, but again, that's just x squared minus 1 to the 3/2. And I'm evaluating that from 1 to 2. Now you got to be careful here. Remember, these bounds are in terms of x, so I need to substitute in for x before I can start plugging in. But it's the upper bound minus my lower bound. So I'm going to have some expression here minus some expression here. You could write the 1/3 in each of them if you want to, but really it's equivalent as if I multiply the whole thing by 1/3 at the end. So it's really up to you what you want to do there. I'm going to write it on the outside here just to save myself some work. So this is, instead of x squared, I'm going to write 2 squared minus 1 to the 3/2. And then instead of x squared, I'm going to write 1 squared minus 1 all to the 3/2. Now it's getting a little crazy with parentheses here, so I'm going to drop some of them. This inside right here, 2 squared is 4 minus 1 is just 3, so this is 3 to the 3/2. 1 minus 1 is just 0, and 0 to any power is just 0, so really it's like minus 0. So I'm not even going to write him. So the question is, how do I deal with 3 to the 3/2? Well, I'm going to reverse engineer that rule. Remember, that's power over root. So really I'm taking 1/3 times the cube root, or excuse me, the square root of 3 cubed, or just 1/3 times the square root of 27. Now, this is going to simplify under the radical. I could actually break that down into 9 and 3. You know, if you really wanted to simplify all the way here, you could. Since you don't have a calculator, you don't have to. Something like this, or even something like our previous answer, 1/3 times 3 to the 3/2, is perfectly acceptable. But just to show you how you could simplify it, I could break down 27 into radical 9 times radical 3. Radical 9 is just 3 times radical 3. And I still got that 1/3 I'm multiplying by on the outside. And 1/3 times 3 just reduces to 1. So really my answer, nice and cleanly, is just radical 3. Now you don't have to simplify that, right? Because this is an irrational number. If you left it as something like this, that's perfectly acceptable too, as long as you clean it up so it's just one term here. That's one example. Let's try an example that works out even cleaner. We'll take a look at number 8, which is just the integral from 0 to radical 5 of x over radical x squared plus 4 dx. Again, I'm going to let u be equal to that guy in the denominator there, and just see what happens. All right, so you should notice the similarities between all these processes. I'm going to take the derivative. Again, I need to get rid of an x and a dx, so I'm going to divide out the 2 again. It's not always going to be a 2, it just happens to be for these couple of examples. And I could always introduce a constant by multiplying it instead of dividing it. That's fair game too. So I've got the integral of 1 over radical u times 1/2 du. Or if I rewrite it, I've got 1/2 times the integral of u to the negative 1/2, right? Because that's the same thing as u to the 1/2 in the denominator there, du. Now I can integrate. I can add 1 to the exponent. Negative 1/2 plus 2 over 2 is just 1/2. And I'm going to go from there. So that's 1/2 times u to the 1/2. And again, instead of dividing by 1/2, I'm just going to very quickly multiply by the reciprocal, which is just 2 over 1. Now you should notice 1/2 times 2 over 1 just reduces to 1. So really the only thing I need to plug into here is u to the 1/2. So what I'm going to do is I'm going to keep going from here. I'm going to plug in my x value, which is x squared plus 4 to the 1/2. And I'm going to evaluate that from 0 to radical 5. Right? I'm going to keep writing over here. I know this is getting a little messy. It's going to be radical 5 squared plus 4 minus 0 squared plus 4. And now, this is a common mistake that I just made, that I'm sure some of you make from time to time. This is all to the 1/2 power. So this is to the 1/2 power right here, and this is to the 1/2 power. But remember, that's the same thing as just being under a square root. And if I'm thinking about simplifying, to me it's easier to think about a square root instead of a 1/2 exponent. So let's try to clean this up a little bit. Remember, if I square a radical, the radical just goes away, right? Radical 5 squared is just 5. And 5 plus 4 is 9. That's good because that's a perfect square. And 0 squared is just 0. Plus 4 is 4. Well, the square root of 9 is just 3. The square root of 4 is just 2. 3 minus 2, look at that, simplifies so nicely to just 1. So generally the ones we're doing, since we don't have a calculator, they will either clean up pretty nicely or very nicely. So let's just try one more example that's going to clean up very nicely. So if I take a look at, I think I called this number 9, the integral from pi over 4 to pi of cosine of 2x dx. So you might be thinking, trig, oh no, I can't do it. Not true. There's only so many values you need to memorize for trig, right? So some of those should jump out to you already. Let's just take a look at cosine of 2x, I can't integrate that normally, but if that was just cosine of u, maybe I can get something going with that. So I'm going to make him u. U is equal to 2x, which in turn means du is equal to 2 dx. But I just need to get rid of a regular dx, and there's no other constant to get rid of. So, man, maybe I should have picked some different numbers, huh? Got to divide out the 2 again to get 1/2 du dx. So my integral is just cosine of u du, and I'm going to write the 1/2 on the outside. I'm going to skip where I write it on the inside. So you got to ask yourself, who is cosine the derivative of? Well, cosine is the derivative of sine. So the antiderivative of cosine is just positive sine. And if I make the substitution, remember u is just 2x. Here's where you need to be super extra careful. When I substitute in these values for x, I want you to notice that there's a 2 in front here that I'm going to need to multiply each of these two. So watch what I'm going to do. This is 1/2 times sine of 2 times pi minus 1/2 times sine of 2 times pi over 4. Let's clean this up a little bit, right? 2 times pi over 4. Well, that's the same thing as 2 over 1 times pi over 4. Or 2 pi over 4. Or if I reduce, 2/4 is just 1/2. So this is just pi over 2. Now, that's pretty helpful to me because pi over 2 is an easier one to remember. Remember, 2 pi is the same thing as 0 degrees, or the same thing as 360 degrees, if I'm thinking about the unit circle, that is this point right here. And remember, for the unit circle, the radius is 1, so that x value is 1, but the y value is 0. So the sine of 2 pi is just going to be 0. Okay, that's pretty helpful. Now, pi over 2, if you have trouble thinking about radians, that's just 90 degrees there. So if I think about the y value at that point right there, well, my x value is 0, but I've moved up 1, so my y value is 1. So my sine value there is just 1. So really, this is 1/2 times 0 minus 1/2 times 1. That goes away, and all I'm left with is very cleanly negative 1/2. So really, the use substitution here wasn't that bad. The hardest part was just plugging in and remembering your trig values. So you will still need to know them for our upcoming test.